The last few months have been pretty exciting from a containers perspective. I don't know if everyone's excited about containers as I am. Awesome. But we've actually seen a lot of interesting developments in the space. The first, and possibly the most noteworthy, has been Docker, which is a very popular Linux application container stack, going into production, so being production ready, which is great. And at Google, we've been working hard to make the Google Cloud Platform the best place to run containers. And we've had two releases. One, we introduced container-optimized virtual machines in May. And we followed that up recently, just a couple weeks ago, introducing an open source scheduler called Kubernetes. And my name's Craig. I'm a product guy. And I'm going to take a few minutes to talk you through Linux application containers. Some of the stuff the people that were cheering probably already know. But hopefully it'll give everyone a better sense of what they mean. And I'll take some time to explain what they mean to Google, like how Linux application containers have really helped us at Google, and where the intersection of these things is going. And then I'll hand off to my colleague Brennan, who's going to go through in a lot more technical detail around the stuff that we've actually put into the market right now that you can get your hands on and use. So let's kick this off and say, what is a Linux application container? What does it mean to people? And at the heart, a Linux application container is a very simple way to package up all of your application pieces into a single hermetically sealed unit that you can then deploy into an environment and run. And it has a lot of really favorable properties that we'll go through in detail. And if you actually step back and just think about what it means, it's really raising the abstraction level. So historically, the abstraction level that most developers have worked with has been at the virtual machine level, the hardware level. And with Docker, virtual machines, you have this idealized hardware that you can run multiple instances on, but it pulls through a lot of other goop. With Docker and with Linux application containers, we've actually moved the abstraction up so that you now have, instead of having an idealized hardware stack, you actually have an idealized operating system. That's a very powerful metaphor. So that's great. Woohoo! Increased abstraction level. Everyone loves abstraction. What does it mean to me as a developer? I'm not actually really a developer, but if I were, what would that mean? Why do you care, right? And the reason our developers care, and the reason I care when I'm actually playing a developer, is this ability to create a static, hermetically sealed unit radically simplifies the process of deployment. It creates a much more predictable and isolated framework to package up your application bits, all of its user land dependencies, and get it out there into this idealized Linux environment. It means that your application is now isolated from other applications from a resource perspective. Its dependencies are all sealed in, and it radically reduces the amount of stress that you experience when you're deploying applications or updating those applications. And a lot of customers I speak to, this is the first epiphany. They say, wow, this has really changed the game. This fundamentally redefines the way we think about operations, and so that's very exciting. The next thing that people encounter is this idea of portability. Okay, this is great. I have this idealized operating system. It means I can produce effectively an executable that runs here or there. It runs in my local development machine in a very lightweight place that I've just set up with Vagrant or whatever technologies. And I can take that same package and have a very high degree of confidence that it's going to work in my bulletproof, enterprise-grade, Red Hat environment or whatever environment that I'm running in, right? And so this idea of portability is huge. But it's not just about portability between your development, testing, and production environments, which might be different. It also offers the idea of portability between cloud environments. And at Google, we're very proud of Google Compute Engine. We've put a lot of time and effort into making it an incredibly robust framework for running workloads. But we want our customers to pick it because it's awesome. We don't want to lock them in. And with these container technologies, it's the first time that customers have really had an opportunity to package up their application in a framework that's portable, that can run in Google Compute Engine or in another cloud or in their sort of personal cloud, their private cloud. And these container formats offer a very high level of portability, which is great. And then finally, when I talk to customers, there's this the pennies kind of dropping around, wow, not only can I think about my application as being sort of hermetically sealed, but I can actually start to decouple it. Take these application pieces and put them together into loosely coupled systems that are much more easy to manage and are much less intrinsically bound together. So instead of having all of these pieces in the soup of an operating system environment, I can tease them apart and control them separately. And I can mix in stuff. I can mix in pieces that are provided by the open source community. And I'm hoping that we'll very soon start to see ISVs, producing commercial software that can be mixed in the same way. Microservices is really powerful. And all that's great. It's really catching on. We're seeing a lot of hype and a lot of excitement around this. Now, it turns out containers have existed for a while, and we've been using them in Google for a very long time. And we've actually approached it from a slightly different angle. We get a lot of those benefits, and we've really benefited from them. But there's a couple of other things that working in this container optimized environment brings. When you're doing hyperscale deployments, like we are, whether it's search or Gmail, efficiency is really important. Being able to get every ounce out of your underlying infrastructure. And because we have very high levels of resource isolation, we're able to pack things much more densely and use very high-level algorithms to do that. If you're doing hyperscale deployments, predictability of deployment is critical. Like, if you're deploying something that is as complicated as the things we do, having to worry about mapping a specific application to a specific piece of hardware just doesn't work. It doesn't scale. And then the quality of service is huge. We are able to, a scaling event for us doesn't involve provisioning a virtual machine. We already have a massive fleet. It simply involves taking a very lightweight thing and dropping it into another environment. And the other thing is it makes our developers better. We have much higher levels of introspectability, and so they're able to actually get a much better sense of what's going on in their code. They can understand what resources they're using. They can understand what contention they're experiencing. And they're able to use that to produce a far, far better, feed that back and actually produce more efficient code. So at Google, we do start over 2 billion containers a week. That's a lot of containers, right? That's 3,000 a second. So when I say everything runs in containers, I mean everything runs in containers. And if you think about that, I've been talking for 7 minutes now. So since I started talking, we've launched about 1.2 million containers. That's a lot of containers. And the thing I'm really excited about is that, thinking about where we're going, we've seen the ecosystem rally around this efficient, this portable, decoupled framework. Inside Google, we've created an incredibly efficient framework that's actively managing your systems, where you as a developer at Google aren't running something. You're writing code, and you're handing it off to these systems that run it on your behalf. And they do it far better than you could possibly do it, because they're constantly watching. It's like a modern flight control system in an airplane. It's taking a lot of signals and making very intelligent decisions about what to tune and what to adjust to make the overall system perform better. And so we get efficiency, and we can bring that efficiency to our engineers and radically drive down the cost of operations. We get performance, like we do with App Engine, which is effectively a container-based solution, where a scaling event happens in milliseconds instead of tens of seconds, which is what you see with Compute Engine, or minutes that you might see with other cloud providers' virtual machines. Continuous integration is really easy. You can build something, you can roll it out a little bit. If things don't work out, you can roll it back very easily. And then just overall, a much more robust system. So we're extremely excited about these technologies, and I'm very pleased to hand over to Brendan, who's a developer on our team who's headed up a lot of these initiatives, to tell you more.
Great. So I'm really happy to give you a guided tour of both how we build cluster management inside of Google and how we're bringing that knowledge to the cloud platform. As a bit of context, I worked in this search infrastructure. I worked in search infrastructure for about 4 years before I came to the Google Cloud, where I got to use this cluster management to provide the backends that provide search for Google+, and for recent events in products like Google News. And basically, anything that you see in Google that is under about 12 hours old is coming out of software that I or my teams wrote. And so I'm particularly excited to be able to take some of the systems that enabled us to build those scale systems and make them available to customers of the Google Cloud Platform. So if we take a look here, this is a basic high-level overview of the Google Cluster Management Stack. It's really split into 2 pieces, and I'm going to deal with each of those pieces individually. At the bottom, we have a node container manager and a managed base OS. This is basically the piece of software, or the piece of multiple pieces of software that are distributed onto every single machine in a Google data center. So every single machine in the data center is homogeneous. Every single machine is running exactly the same set of base infrastructure that allows it to execute arbitrary containers. Now, on top of that, the software that runs Google Search or Gmail or anything else that you use, Docs or anything else, runs inside of a scheduled container. Now, that container didn't end up on that machine because a developer said, oh, I want to put this on this specific machine, on this specific rack. It ended up on that machine because the developer said to the cluster scheduler, the master for the cluster, I have this amount of work. I would like to run 10 copies, 10 replicas of this piece of software. It needs 3 cores and 10 gigs of memory and a little bit of disk. Find me a place where I can exist happily. And the cluster scheduler takes care of things like figuring out that it should do spreading across multiple machines in order to avoid a single point of failure. It does things like do resource isolation, so it understands that I only have this number of cores on this machine. There isn't enough free cores there for me to be able to schedule your job there. And it does all of this on my behalf, and so I can have this declarative, abstract, high-level concept of a piece of software and a set of resources, and the scheduler can make that happen. All right, so for the next 15 or 20 minutes, I'm going to sort of step you through how we're bringing these concepts out and making them available to people inside of the Google Cloud Platform. And I'm going to start by talking about the Node Container Manager. So if it switches. All right, so the Node Container Manager is a system for the cloud platform, at least, that we released in the middle of May. And basically, it's a container-optimized virtual machine. It's just a single virtual machine image that has been built with software that makes it really, really easy to run a container on that VM. We've standardized a declarative container manifest, which is a declarative statement that basically specifies the software that you would like to run on this machine. And it also does health monitoring and some reliability to ensure that if you ask for something, and one of the reasons why we're really interested in declarative representations is that the statement says, I would like this thing to be running. It doesn't say, please run this thing. It says, I would like this thing to be running. And that means that the responsibility for making sure that that container continues to run through failures, through other problems that might cause it to stop, has been handed over to Google. You no longer have to worry about, is this process actually up and running? The infrastructure on the container VM takes care of making sure that that's true. So we're going to take a little bit of a deeper dive into this container-managed VM. And we start with basically looking at a very simple example of how you might create one of these using Google Compute Engine. This is basically, there's a large amount of text there, but basically what it is doing is it's creating a virtual machine in the US Central 1 zone. It's an F1 micro, one of our small instances. It's using the container VM image, and it's setting a metadata key from a file. And that file is the containers.yaml that contains the actual declarative specification of what it is that we would like to run. Now, that containers.yaml here is a very simple, stripped-down representation of all of the things you could express, and we'll go into a little bit more of the details in the next few slides. But what this is basically saying is I would like to run a single container. I'm going to call it dub. It's going to run Nginx. That's the software that I want you to run inside of it. It's a sort of lightweight, high-performance web server. And I want to expose a port. In this particular case, it's going to be the HTTP port that's mapping a port inside the container on port 80 to the external 8080 container. So that means that when I create this VM, it's not just booting a virtual machine. It's actually installing this container. It's starting it up and running. And by the time that this container-optimized VM is done, you have a reliable web server running on port 8080 that can start serving your traffic. And if, for some reason, either due to a programming error or to someone accidentally killing that process on the VM, the process dies and the container dies, it will be automatically restarted. And so you can be assured that your web server will continue to function. So in some cases, we actually may want to have more than a single port. Web servers often serve both HTTP traffic and HTTPS traffic. So here's an example expanding on the previous declarative specification. Now we're adding a second HTTPS port. In this case, we're not actually remapping the port. We are simply keeping the port 443, the standard HTTPS port. So we have the ability to have essentially arbitrary network ports. And again, Craig mentioned that introspection is a big part of why we like containers. And ports are a great example of why this introspection is valuable. So I can actually walk up to this VM now, and rather than just treating it as a black box operating system, where in order to understand what software is running on it, I might need to run an invasive tool like a port scan or anything else like that, in our UI, we can actually walk up to this VM and see, aha, they're running a web server, they're running an HTTPS server. Maybe we'll add some links that allow you to just drive directly to that as part of what the container VM looks like. So having this extra metadata, this extra information about the kinds of applications that you're running on a VM actually enables the Google Cloud Platform to provide a better, richer experience that actually gives you deeper insight than just, oh, hey, we see that there's a virtual machine running here. So that sort of gives you a brief example. I wanted to step into a slightly more complicated example of one of these declarative manifests. This is a pattern that we see emerging a lot internally inside of Google and that we think we see also happening in the exterior world, which is we actually want, and this idea is the notion that we have containers that actually work really symbiotically together. They're containers who, in this example, we may have a web search front end that actually answers your queries, the thing that actually receives the request and gives you back the documents that match. And it has a symbiotic data loader container that is always looking out into the network, finding new data shards as new documents. I mentioned I worked in freshness. As new documents are made available, new shards are built. The data loader is responsible for taking those things off of the network, bringing them onto local disk so that the search engine can actually serve those files out to user requests. Now, these containers have very, very different resource requirements and very, very different quality of service guarantees. Obviously, we want the searches that people do to be as fast as possible. And so we want to ensure that the web search container has high quality of service, very, very low latency. The data loader, on the other hand, it's a background batch processing job. It's responsible for keeping the server up to date, and that's a very important function. But if it gets delayed for a few seconds while we're in the midst of handling a burst of queries, that's OK. And so having these things in two different containers with two different resource isolation boundaries allows us to apply different levels of quality of service to the two different containers and have a really responsive user experience that may actually steal some resources from the data loader when necessary. The way that these two containers communicate is through a shared volume. So you can see at the very bottom there, we have this volume that's named data shard. This volume in the container spec basically means that we will create a shared directory that is mounted into each of these containers where the shards are going to be living, so that the data loader can copy the files into that directory, the web search software can read from that directory and load in new searches. So it's load in new data to serve searches. So it's a shared object, a shared piece of storage that both containers can see and can use, and yet the two containers are still isolated from each other because they cannot see any of the rest of the configuration files or the application binaries or anything else that might be inside the container. So you only share what is necessary to achieve the symbiotic relationship. You don't have these two things in the same place where they might accidentally clobber each other or anything else like that. So this is an example of how you might build a relatively sophisticated single node application on top of the Google Container VM. Oh, I think I hit the back button. All right. So I wanted to give you a little bit of an illustration of what's actually happening on that VM. On the left-hand side, yes. The left-hand side, you see the stuff that Google provides. This is the operating system, obviously, the monitoring and logging agents. The Docker daemon is installed as well. Tools like SSHD or the init system are all part of the sort of software stack that Google is providing as part of the container-managed VM. In the user experience side, well, we're going to provide you with a container environment. This involves things that you may pass in, like environment variables, the ports that you want to open. And then, of course, your code is going to actually be running inside that container environment as well. So this is how we really have taken a lot of the concerns about running a piece of software. We've offloaded it onto the Google-managed VM, and we have made your code the thing that you really focus on running. All right. So that gives you an illustration of the node-level single machine management. But really, if that was the place that Google started or stopped, we wouldn't have to have these giant data centers that are full of all kinds of different machines. The really interesting thing that happens is, well, suddenly, what if I have thousands of machines and I need to be able to say, well, I have this set of containers. Could you just make them run somewhere? And so the job of the cluster scheduler is to absorb a set of resources, make it available to the user as an abstract compute substrate, an abstract pool of compute that's available, and then schedule work out to those into that large pool of resources. And so this system has been developed over a number of years at Google as we needed to push utilization, as we needed to improve the developer experience. And so about 2 weeks ago, we announced a project, an open source project called Kubernetes. It's ancient Greek for pilot or helmsman of a ship. And it's an open source cluster manager that tries to build on some of the ideas and patterns and paradigms that we've developed over 10 years of managing containers at Google and make those ideas available out into the community. Now, at the same time, we understand that the containers that people are using right now are not necessarily the containers that we've used internally inside of Google. And so we really wanted this open source project to not just sort of be a data dump or a knowledge dump of the stuff that we've learned, but actually an opportunity to explore and expand and learn with the community. So I'm going to spend the rest of the talk basically stepping you through Kubernetes, giving you some examples, and finally doing a demo of the system. All right, so Kubernetes provides that scheduler layer. It provides the master scheduler binary. It provides a set of machines that are all identical. They're running that container node piece, the container manager, on each individual machine. And it provides this unified substrate that you can schedule work into without really caring what machine it lands on. So for example, I may have a pod like that I was talking about before, where I have a web server and a symbiotic task, which is its log roller, right? We can't let our log files accumulate and accumulate and accumulate. We eventually will run out of disk. We need a log roller that's going to be responsible for truncating a log, shipping it off to a system like BigQuery, or a more persistent cold storage like Google Cloud Storage. So these are symbiotic containers that work well together. The web server, obviously, low latency, serves user traffic. The log roller, batch background kind of task that's responsible for sort of maintaining the health of the container. Again, sharing resources through a shared data volume. Now, I, as a developer, define that declarative representation of, here's my web server container, here's my log roller container, and I go to the master and I say, hey, this is what I'd like you to run. And the master is the thing that's actually responsible for saying, aha, I have this container VM over here, it's available, I'll put the work on there. All right. And so if this was all you were doing, if you only wanted to run a single task or a few tasks, this might be where you stopped. And indeed, this is where you could stop if you wanted to with Kubernetes. You can simply use it as a way to schedule work out onto a cluster of virtual machines. But what we've found internally is that once you start scheduling jobs and once you make it really, really easy for users to schedule work out into their own personal cloud, people start scheduling a lot of pods. Right? They start scheduling, if you think of Git and having, in my traditional Git client, I have 10, maybe 15 branches. I can deploy each one of those branches as a hermetically sealed container running out in my cluster. And so pretty soon I do that. And I have lots of containers running all over the place. And it becomes very, very hard to understand the system and to reason about the system. That one list of containers that contained 4 pretty containers now contains hundreds. It scrolls off the bottom of a page, and I need a way of organizing this information. And the way that we do this inside of Kubernetes is the notion of a label. All right. So a label is basically just a query that you can execute across a set of containers that is keyed off of properties of those container, key value pairs that are properties of those containers. So you can think of this as being sort of like a selector in a UX framework like jQuery, or any number of other kinds of querying usages. So for example, here I might have a label query that says, I would like to select everything whose role is front end. And you can see in green now, I have selected all of the front end jobs that are running inside of my Kubernetes cluster. Well, this is only sort of useful because indeed, some of those front ends might be development front ends. Some of those front ends might be my neighbor's front ends. I actually maybe don't care about a lot of them. And so label queries can be conjunctive. And so I can expand on this label query and say, OK, actually, I'd like the labels of the role is front end and the stage is production. And you can see now all of the front ends that have dotted lines around them have dropped away. Right? I put dotted lines around them to illustrate where they had been in the previous query. And the only front ends that are left now are the front ends that match both the role being front end and the stage being production. And so now I have a really elegant way that I can slice through. I can say role is development cluster, user is Brendan. I can slice through all of the things that I've scheduled out onto these machines and find exactly the kind of thing that I'm looking for. And again, one thing that's important to realize is that I've stopped viewing all of my containers as things that are on particular machines or things that are running in any particular place. I've really started to think of my cluster as simply being this one giant resource that a bunch of things are running on. And I stop really having to worry or care about specific locations. And that's a pretty powerful abstraction. All right, but label queries are nice for UX and for looking at things, but they're really nice when you start using them as building blocks for other services. So one of the very first things that you want to do once you have a single pod, a single set of containers that work well, is you want to scale it out. This is where you've stopped doing development and now you're moving towards a production or a beta system. You say, you know what, that's the thing. I want to cut out 10 copies of that. I want to have a cookie cutter, and I want a bunch of copies. And we can use labels as a way of organizing this with a notion that we call a replica controller. And so a replica controller basically is the combination of a label query for identifying what containers you want to run, a template, the cookie cutter, if you will, for describing the thing that you would like to cut out, and a number, which indicates how many of that thing you would like. And so, for example, here in this declarative configuration of this replica controller, I have 4 replicas. The template is elided for space. And then I have a label query that says, and the role is front end and the stage is production. And the reason that the label query is important is because this object that is responsible for the replication is actually an active object. It's a live reconciler that is part of the system. It's not an imperative sort of execution of, oh, I'm going to go, and it's not a for loop that's going to go and create 4 of these controllers. It's an active object in the system. It's one of these flight controllers that Craig was referring to that's responsible for ensuring that there are 4 of these things always. And so you can think of it as constantly running a loop. And the loop says, execute label query. OK, how many containers did I get back? I only got 3 back. It says that I should have 4. Let me create a container. OK, now I'll cycle again, do the label query again. And now I have 4. Great, I have 4. I won't take any action. Do the label query again. Wait a minute, I have 5. How did that happen? Kill one of those containers. Now I'm back to 4. So this is a live object that lives in the system. It means that the system is self-healing. It means that adding properties like dynamic resizing, as we'll see in the demo later, becomes very, very easy and very natural for the system. This notion of a reconciler and of an active controller inside of a cluster manager is a very, very important concept that's core to a lot of what we do at Google. So the second thing that we introduced that lives on top of that label query is the notion of a service. Oh, excuse me. I'm going to step through my slides. I spoke over my slides. Go to 1, go back to 3. All right. Now we go back to a service. Excuse me. So the notion of a service says, well, you know, it's great that I have this replicated set of things, but any real application that I build needs to be linked together, right? I don't just have front ends. I have front ends and back ends. Maybe I have front ends and back ends and middleware. But if I have this replication controller that is dynamically resizing things, I don't want to have to reconfigure everything. I don't want, if I take the set of back ends from 2 to 6, I don't want to then have to reconfigure my front ends to understand that there are 6 back-end servers now where there used to be 2. And so the service abstraction allows you to have a named load balancer that automatically balances load across a label query, a set of containers, and it provides a single network endpoint that your front ends can talk to. And this all happens automatically inside of the Kubernetes system. You declare a declarative representation of the service like this, backend service. I want it to run on port 9000. Here's the label query. And Kubernetes for you creates this service endpoint on every single host machine in the cluster, so that on any machine, if you access port 9000 and you open a connection, you're going to be transparently load balanced to one of the containers that match this label query. Right? Again, the organization of these containers means that I can build up these abstractions where I just don't have to care about the details of my system in places where I don't need to. All right. So with that in mind, I wanted to give you a brief demo of the system in operation. Try not to trip. All right, so I'll jump out of the web browser and into my demo over here. OK. Is that visible? Reasonably visible. All right, so you may recognize the fellow looking out at you. I have here 4 containers. This is a replication controller running 4 containers. They're simple image servers. They're serving out a very simple image. You can see this is the container ID. So the container ID is different for each one. And this is the IP address that they happen to be running on. And so the very first thing I wanted to demonstrate is some of the self-healing properties. And so I'm going to go over here. And I'm going to SSH into of the machines. Oops, that's not going to work. I just say gcutil. SSH into one of the machines. All right, and so if I say sudo, if I do sudo docker ps, we can see that there's actually this Nginx web server that's running that's serving up the data. All right, so I'm going to move this aside so that you can actually see, because this effect is actually, the health check restart is quite quick, and so it's somewhat difficult to actually see it, and we may in fact not see it. I will stop but note what the Docker container ID is. I'm going to stop that container, simulating a failure. You can see that the image is no longer being served. But the system, the agent that's running on this VM is going to notice that that container is stopped. And I'm going to restart that container, and now the image is back and being served. And if we do that PS again, you can see that we have a new container here. It's only been up 8 seconds now since I killed the other one that had been up for 3 hours. So that kind of health checking on the node means that you don't have to worry. You can simply say, I want this thing to be running. And the cluster manager will take care of ensuring that it actually is running. So the next thing that you might want to do along these lines is you might want to actually resize. I'll move this up again so there's better visibility. You may want to actually resize. 4 of Craig is just a little bit too scary. And so I'm going to go over here, and I can actually say cloud. This is the tool. So it's worth mentioning, Kubernetes has a RESTful HTTP API. So you can write arbitrary clients that communicate with this API, create new containers, create new services, create replication controllers, resize replication controllers. It ships with a simple command line tool that allows you to do these things, but you're free to build any kind of orchestration on top of it. So I'm going to say cloud config, resize, data, if I can type, controller 2. And so now it's resized this down. It's actually killed 2 containers there. They're no longer running on those machines. Now I only have 2 of these images. Well, maybe that was a little bit harsh, and we actually would prefer to have 3 of Craig. So we will resize back up to 3. And here now we're going to see a little bit of a blip while that container killing is fast. Recreating is slightly slower because it's very easy to stop a process. Actually starting the process, getting Nginx ready to serve takes a few seconds, as you saw. So now we have 3 containers running inside of Kubernetes, all scheduled onto specific machines. But again, we don't really care about that particularly much. Now, the other kind of lifecycle that you might want to do, in addition to resizing, is actually editing the kind of thing that you're serving. So I wanted to give you a little bit of an illustration of what workflow might look like. Workflow does look like inside of Google, and workflow might look like for you out using Kubernetes. So I have in this directory is the Docker image, the container that's running on these machines. I'm going to open up the data file. And Craig, a little scary, so we'll replace this with Brendan. Nice, friendly developer, not product guy. So at this point, I can say docker build-t Brendan data dot. So this is building up my Docker image. I'm going to push that. OK, one of the nice things about this decoupling of the container image from where the container is executing is that this activity of actually updating my container doesn't actually change the running service. So as you see the image slowly being pushed up, you won't see any changes in the running service. And indeed, even when the push is completed, there won't be any changes in the running service. I've separated out application update from running service update. So application update is this atomic thing that happens with me pushing a new package somewhere. Service update becomes a new atomic thing that has to do with running that new container on my cluster. And by partitioning them in these ways, I have much more reliability in both. If the application upload fails, that's fine. I can redo it. If the cluster update fails, it's very easy for me to roll back to an old version of the same application. I don't end up in states where I'm sort of partially installed and it's impossible to get back, and I may not even get a clear signal about whether or not I succeeded. All right, so my image has been updated. I'm going to go over here. And I'm going to say clear so everyone can see. I'm going to say cloud config.sh rolling update. Let's say -u, 15 seconds. And so what this is saying is I want to do a rolling update. A rolling update means one container at a time. I'll bring it down, bring it back up with the update. I'm using an inter restart period of 15 seconds, way, way, way faster than I would recommend anybody doing in production. But I don't want to have you sitting around for 5 minutes while we restart containers. So we'll start this off, and what you're going to see is as this runs, that container went down. It's going to be starting back up. I'll go back. And with luck, as it starts back up, there'll be a friendlier face to be seen. We'll keep our fingers crossed. The tension is starting to kill me here. It's actually having to pull the image. The previous restarts, yay, there I am. The previous restarts didn't have to pull the image. It was already on the machine. These machines actually have to pull new data down from Docker, so there's a little bit of a second while we pull the image off the network. So that last one should finish booting up with any luck. The update is finished at this point, and in a few seconds, the update will complete. So that's really a demo of some of the flexibility. When you stop thinking about virtual machines, you start thinking about containers, you start thinking about scheduling containers and scheduling work out onto this homogeneous pool of resources where the machines really disappear and you start just thinking in terms of CPU, memory, and the software that I want to run. And you add on top of it some management concepts that provide the right kind of abstractions for both the lifecycle things you do in your application, as well as the ways that make linking pieces of your application both decoupled and easy. You start being able to build applications the way that we've built applications inside of Google for many, many years. And so with that, I'll jump back into the presentation and hope that I grabbed the right clicker. All right. I wanted to give a little bit of an example of how you might build a more complicated application. That application was really just a single container. Here's an example of a more complicated guestbook that you can find on the Kubernetes GitHub. And in this case, we have 3 front ends controlled by a front-end replica controller, talking to a service that's defined as a Redis slave service, being read slaves, talking to a replicated set of Redis slaves, talking to a master service that lives on top of a single master. So this is just an example of how you might build up a more complex tier of applications. All right. So I just wanted to end by saying we've thought a lot about containers and how you build and manage containers and cluster management systems over the last 10 years. I'm super excited to launch this open source project out to the developers community in general and being able to take the step forward together with everyone else for how we're going to manage containers for the next 10 years. Thanks very much. Some links. I wanted to also add, as a gift to everyone, and you may have seen this already, you've got a $500 credit for the Google Cloud Platform. Go and use it to build out your best and brightest ideas. Thanks. All right. And I think we have about 6.5 minutes left for questions and answers, so I'll bring Craig back up, and we can ask. Sorry. All right. Yes, I'll leave you with the important thing. I don't know, pictures of me might be worth more than 500? No, probably not. Too bad. All right, so if there are any questions that we can answer. Yes?
I would like to know if you can manage quota async to a container when you use a container YAML. I mean, if you can async some limited memory or CPU to various containers you deploy side by side.
So currently, the container manifest does not allow you to do that, but it's an evolving API and an evolving standard, and so we will definitely be building towards doing that. And you could even send us the pull request.
Hi, my name is Maciek, and I would like to know if I can use Kubernetes in my own private cloud.
Yes, absolutely. We want to make sure that it runs really, really well in the Google Cloud Platform, and we have developed it on the Google Cloud Platform, so you'll find that that's the most seamless experience. But we've actually already we have both a local development environment that will run on your machine, a single cluster, if you will, a single node cluster, if you will. And we've also had people deploy it onto their own machines as well.
And what virtualization technologies do you support?
Sorry,
Do
what?
you support VMware, KKVM? What virtualization technologies?
So we actually do not use virtualization. If you happen to deploy it onto a set of virtual machines, then it will work. But if you deploy it onto bare metal, it will work as well. So the underlying container technology is the Docker container technology, and there's a number of different backends that can be used for that container. Did that help answer the question?
Do Kubernetes spin up virtual machines automatically?
The scripts that we have currently will spin up machines for you in Compute Engine. But there aren't any scripts that spin them up for other platforms. Again, because it's an open source project, we very much welcome contributions from other people who want to be able to make it work on.
And we are working with the broader community. You'll see over the next few weeks, I think support for other providers will spring up because the community demands that.
Right, absolutely.
Hi, my question is related to container optimized VMs versus plain VMs. So when I actually spin up a normal GC VM, nothing stops me from installing Docker and using Docker run to actually launch a container versus a container optimized VM where I can actually use the YAML file, which is going to be the metadata for my Docker container. So is the difference primarily in the YAML file acting as a startup script, or do you do anything beyond that? So is it just a convenience that you provide to the agent and the startup script, or does it have further optimization within the VM?
So I think that convenience is a big part of it, actually, to be honest, right? Like, we definitely want to make people think about running containers, not running VMs. And so if you can simply start thinking about the thing that you're running as being a container, I think that's a good thing, and that's a huge thing. But there's also a lot of software that we've installed onto that VM that make running a container better. And that includes things like CAdvisor, which is a program that some Google engineers launched at DockerCon also about 10 days ago, which is a way to get really rich statistics about what's going on inside of your container. That includes the agent, the onboard agent that's responsible for health checking and automatic restarting of the container. There's nothing that prevents you from installing these things yourself. And so you could build an analog of the container-optimized VM manually yourself if you wanted to. But we're going to curate this thing going forward, and really we're going to do our best to make sure that that VM is the best experience you can have for running containers on the Google Cloud Platform.
So without Kubernetes, the container-optimized VMs are basically plain vanilla GC VMs with agents and some extra startup scripts, right?
That's correct. They're really static. They're really static VMs without the cluster management layer on top of them.
And we'll produce a nice tooling experience so that when you actually want to just go from the command line or from the UI and want to get a container running, it'll be a very slick experience.
Right.
So my final question, will Kubernetes show up on the developer console any day?
It's available on GitHub right now as something you can install yourself.
No, the developer console, the UI to deploy and manage containers.
We can't signal where we're going exactly, but it would be reasonable to expect that we would have a hosted version of this in the not too distant future. It's actually worth mentioning that what we're really looking to do here is to engage the community. We want to, you can tell where we're going with this stuff, right? This is the way we've been running our internal workloads. And by reaching out with Kubernetes, we're putting an API out for conversation. Help us shape it to be the thing you want. And we'll provide the fully hosted version of it that's running in our framework. And that's ultimately where we want to go with this.
Great, thank you.
Hi. So if I understood this correctly, every container speaks only to other containers via a service abstraction. So it has no knowledge of the other containers running. So, and since it's only talking to a service, you can scale it out. Now my question is, this only works if the individual containers talk to other services but are stateless. What happens if you want to do data sharding, for example, in which case you would need to speak to a specific container to access a given shard? So do you have a Zookeeper-like mechanism, or how do you manage this?
Sure. So just a little bit of a clarification. There's nothing that precludes a container from talking directly to another container. And indeed, you could talk to the API and introspect it and figure out what containers are running, or you could hard code some sort of configuration in. I think that we think of services being convenient ways to link things together, but they're definitely not the exclusive way to link things together. I guess the other thing that I would say is it's come up in other contexts inside of the community about providing richer semantics for that service. So right now, that service is a round-robin load balancer. But you could imagine being able to define a service type that is a master-elected balancer that only ever takes your traffic to the current master, or a sharded. Sharding becomes trickier because you have to have some notion of what the sharding function is, right? And so that becomes a trickier concept to put in there, but you can imagine these primitives becoming richer in the future, or you could just simply bake your own.
So. Okay, thank you.
Mm-hmm.
Hey, sort of building along that, we built our own similar kind of concept for deployment where we tried to abstract away all of the messiness of what it was you were running on. And we started out with a declarative syntax, but it rapidly became clear that if we wanted to take advantage of existing software, like they had their own peculiar workflows and configuration and everything. For example, like Mongo, like trying to containerize Mongo, we ended up going with an imperative syntax just because, like, if you've got, you know, multiple shards with their own master, you know, their own triplets of voting rights and things like that, it gets to be a fairly complicated dance to get it set up. And so sort of along the lines with the previous question, is there anything built in for sort of identifying in an abstract way, like you kind of had the idea of roles as labels, but you like sort of having staged workflows for, okay, everybody needs to get to this state and then run this set of stuff, and then now everybody's in this. Oh, and now you've advertised yourself as ready, so we can add you to the load balancer. Is there anything along those lines, or are you heading in that direction?
I guess I would say that I would, if we were to build something like that, I would like to see it as something that lived on top of this API rather than being something that existed within this API. I think that I could imagine some degree of orchestration within a pod, where you might say something like, this is an initialization container. Please run this initialization container to completion and then start the server. But I think when you're starting to talk about like really significant workflow, that kind of system is probably better served by being something that lives on top of the scheduling API rather than a part of the scheduling.
I would completely agree with that. You know, I think the ideal here is to provide a really useful generic scheduling API, and then provide a framework so you can create abstractions on it. So you'll be able to identify something within that, get a channel to that, communicate with that in a way that makes sense to you. But that does need to be a strict abstraction on top of the system. I think that's exactly right.
It sounds like the container-optimized VM has a lot of similarities with CoreOS, and they strive to be like in an ideal environment for containers to run. Can you speak to some of the differences between those two projects, or advantages and disadvantages?
I mean, I think philosophically they're definitely very similar. I mean, they're machine images that are optimized to run containers. You know, I think there's some stuff like CAdvisor that, you know, isn't present on CoreOS right now. Maybe it will be. And again, I think that this is a place where one of the reasons for getting out there into the community with an open version of this is to really engage with those sorts of people and see if there's a consensus around what the node image should be, see if there's a consensus around what the declarative syntax for scheduling tasks should be. And if we reach a place where there's, you know, a POSIX standard or whatever that happens to be for what a container machine looks like, I think that's a great place to get to.
Yeah,
so you could see a convergence.
Yeah, I would, let me just sort of step back a little bit. I'm completely agree with Brendan, but think about what we're doing here as a pattern that we want to engage the community around a conversation on. So we will offer up a container-optimized VM. We fully expect a lot of other providers to provide the self-same. You know, that, you know, you could expect the regular players to come up with that. We want to engage the open source community in a conversation around what the right set of abstractions, what the right set of interfaces are. And we want to make sure we're open and not opinionated. So, you know, we love the guys from CoreOS. We love the guys from Docker. You know, we're spending a lot of time working to bring our expertise to operationalize it. And what we're hoping to do with Kubernetes is to, and with the container VMs, is to start the dialogue and figure out what's great. Maybe they'll take some of our patterns, maybe we'll take some of theirs. But it's just a great starting point.
I guess I would also say that I think that CoreOS, and I'll let people finish, but CoreOS also basically uses systemd as their abstraction layer on their machines, and so it's less container introspectable at some level. You can't really walk up to a CoreOS machine and say, what are the Docker containers that you're running? You say, what are the systemd units, and then extract from the command line, oh, here's the Docker things that I'm running. I think we wanted to take a more declarative approach to the introspection as well, and really be able to ask for concrete information from the machine.
And whenever we can, if you look at the way we're sort of engaging this community, we're getting really strongly behind things like libcontainer, and we're actually putting a tremendous amount of effort into it because we think it's the right abstraction. With something like Kubernetes, we want to create an abstraction that we think is the best possible abstraction out there, and a lot of it's based on a decade of experience running containers. So we don't do this lightly, but and we want to absolutely engage the community and have the conversation around what's right for the community.
Oh, I think we are out of time. So, but we'll take, if you have a quick question, then absolutely we'll have people
come up. We'll be around.
How does Kubernetes scale? Is there a Kubernetes of Kubernetes? If there are more than one Kubernetes, how does they share their information or the status of what they are handling?
So right now, the way that it works is the premise is you give us a set of resources, 50 VMs, 5 VMs, whatever it happens to be, and we'll manage work on top of those machines. So in some sense, you have to have some sense of the resource usage you may need. But it's also the case that you could turn up 2 separate clusters that would be essentially completely unaware of each other, right? They are hermetically sealed clusters in and of themselves. And so if you ran out of resources, you could turn up another. Although we would anticipate that what you might actually want to do is tear down your old cluster and turn up a larger cluster and migrate your containers across.
And one thing I'd say is, when we designed Kubernetes, the intent was to produce something that was simple, lean, and extensible, right? We wanted to use it as a segue to have a broader conversation. So a lot of the things you might expect in terms of, very high levels of scalability, very high levels of redundancy, are not yet present in that offering. We absolutely expect the community and us to work towards that. But whenever possible, we favored understandability and simplicity over this very complex system because we wanted to have the dialogue. And frankly, for a lot of customers where they are today, they have relatively humble needs. And having something that's extremely accessible is a very good thing. And that's how we designed it from the start.
Yeah, absolutely. All right. Cool. Well, I think we are completed, but please come up and talk to us afterwards, and we'll be around at the conference.
Thank you so much.
Have a good time. Thank you.